recall visible light, it's in between infrared and ultraviolet. It's the only electromagnetic wave that is visible. The longest wavelength is red, and the shortest wavelength is violet. Alternatively, lowest frequency is red, and the highest frequency is violet. I should have already copied this down from yesterday, right? So, when light enters a new medium, it bends and refracts depending on its wavelength or frequency. Each wavelength bends at a different amount, and you can use something called a prism, which is just a triangle-shaped piece of glass, to separate white light into its corresponding colors. And it would be based off of its wavelength or frequency. Both either are frequency or wavelength. You can remember the order of the colors by using Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Do y'all know the order of the colors? And keep your mask on. So if I were to ask which has a shorter wavelength, yellow or green? Yellow, because red is the shortest wavelength. You can remember it goes radio waves, microwaves, infrared, then Roy G. Biv, then ultraviolet, X-rays, and then gamma rays. So the shortest wavelengths are on the left. The longer I just said that backwards. Shorter wavelengths are going to be on the right. Violet has a shorter wavelength. I just assumed you got it right. So, shorter wavelengths is going to be violet because gamma radiation is the shortest wavelength. Radio waves are very long, on the size of buildings and people. Red has the longest wavelength. So, out of the choice between yellow and green, green would have a shorter wavelength and yellow would have a longer wavelength. Shorter wavelength and higher frequency corresponds to having more energy. So gamma radiation has higher energy per photon. Radio waves have less energy. So ultraviolet will carry more energy than visible light and has a shorter wavelength and higher frequency than visible light. So the more energy light has, the more impact they'll have if it collides with linear atoms. Once you get to ultraviolet, they start having enough energy such that they can actually start knocking electrons off and breaking down and destroying DNA. UV radiation can cause cancer and hurt you. Enough UV radiation on your skin, you can get skin cancer or sunburn. Yes. Whenever you go into the sun, the UV light that actually damages your skin. Yes. So UV light can be used to kill bacteria and sterilize equipment. Something you use to what? Yes, you can use it to cure resin. It's also what black light emits. To some degree. Again, if you really wanted to kill bacteria, you would have to output a lot of UV radiation, enough that would also damage your skin. Yeah. They actually have in some clean rooms, they have UV lights all around it. So too much can cause skin cancer. Why you should use sunblock to protect against UV rays. But it's also required that you get some degree of sunlight. It doesn't emit it. A chemical in your body absorbs it and uses its energy to make vitamin D. And keep your mask on properly. Mm-mm. Cancer. So it causes your skin to produce vitamin D. You don't need much exposure to UV light to produce enough vitamin D. Going outside for about 5 minutes is sufficient. It says it on the screen. Good for teeth and bones. Calcium. Yes. But to use the calcium, you need vitamin D to help in the construction of it. So X-rays, they're shorter wavelength and higher frequency than UV, and can carry a lot of energy. They can also penetrate a lot of matter. So flashlight, for example, if you shine it on the wall, you're not expecting the flashlight to shine through the wall. However, if you had your flashlight that's emitting X-rays, most of those X-rays would actually go through the wall. X-rays are very good at penetration. Not many things reflect or absorb X-rays. There are a few. Can y'all think of something that would reflect or absorb? Lead is one. What's another one? Mirror one. Oh, guys, come on. What do you use X-rays for? Bones. So bones and teeth absorb X-rays. The light part of the X-ray indicates the place where an X-ray was absorbed. So basically, you have a material. You have like a film on the other side, and it turns black whenever X-rays hits it, or turns clear or transparent. And areas that don't receive any X-rays because it was absorbed by bone wouldn't do it. No, it should go through most clothing. It's absorbed by bones. In an MRI because it's a giant magnet. The metals though will distort the image, and you usually have to remove all the metals because some metals, like lead, absorb X-rays too. And they've taken pictures. They usually, if you come in with like a knife in you, so they'll sometimes take X-rays to see where the knife is inside your body. Or if you come in with a bullet in you, they'll take an X-ray to view where the bullet is. Because metals also absorb X-rays too. So too much exposure can cause cancer. Yes. Yes. A lead vest at dentists prevent organs from unnecessary exposure. So lead kind of blocks or absorbs X-rays. So we can tolerate some amount of radiation. Again, our cells have repair mechanism. The more exposure you get, more radiation you receive, the chances are that it'll turn cancerous or do damage. That's has a lot of what? I mean, most of them, I don't know of any that really get it. But they are getting a lot of radiation. You can't with radiation. It's like fire. So if I were to take a lighter and put my hand over it, I mean, I should show y'all. So if I were to get a lighter and run my hand through the flame, nothing bad happens. Because, again, I'm touching the fire. But if I sit there and hold it, I will eventually burn away all my skin. It's amount of exposure. So when I run my hand really quickly through it, I'm not receiving too much heat. I'm not receiving too much of the energy. However, if I sit there and hold it, I'm going to be absorbing a lot of the heat. And a lot of the heat will eventually kill all the cells in my hand. So engineers use X-rays to look for microcracks, or tiny little cracks in structures. The X-rays pass through the cracks as if they're not there, and they appear as black spots. And areas that absorb, such as the stone, would appear white. So they can find cracks in concrete walls and in the ground. Uh, Depends on whether or not the drywall can absorb X-rays. I don't know if drywall can. So in here, the concrete is able to absorb X-rays, and the cracks or empty voids don't. So they allow more X-rays to pass through the cracks. Because the image is showing where X-rays were absorbed. So the white is where it was absorbed into the concrete. The black is where it wasn't absorbed and was able to pass through. Yeah. So white's the concrete and black is nothing. Hence, yes, because your bones absorb it. Gamma rays have the highest amount of energy and can penetrate most most things. You need like several feet of concrete and lead in order to stop gamma rays. You also don't want to get any gamma radiation on you because it's very energetic and will destroy, it's almost guaranteed that it'll destroy the DNA in your body. Very carefully. A lot of engineering. So they have the shortest wavelengths and the highest frequencies. It's very lethal. Because it's telling you it's important to know that's the greatest amount of energy. And it's also used in radiation treatment to kill cancer cells. It can be very harmful if not used correctly. So just like normal light, we can focus light down to a single point. And we can make a laser that shines on a little tiny point. We can focus gamma radiation down to cellular level, and if we have a microscope and we were to aim it correctly, we can actually pinpoint cells and kill them. If we can identify which cells are cancer cells and which cells are healthy cells, we can use like a gamma radiation laser and go in and manually kill all these cancer cells. You have to be very careful as, again, it can pass through most material, which means it can pass through your body very easy, and you're basically shooting a laser. How they end up doing is they have multiple lasers, and they all converge to a single point. They will pass through that, and you try to limit how much healthy cells you're killing while you're killing cancer cells. Yeah. So exploding nuclear weapons emit a lot of gamma radiation. And keep your mask on. No, they just convert mass into energy. They're complicated. They're also formed when a star dies, whenever a black hole eats up another star. They're produced in highly energetic conditions. So all electromagnetic waves travel at 3 times 10 to the 8 meters per second. They all have different wavelengths and different frequencies. Long wavelength corresponds to lowest frequency. Short wavelength corresponds to higher frequencies. And higher frequencies correspond to energy. So energy of a photon is directly related to its frequency. So the faster it's bouncing up and down, the more energy it has. Because it has to have a large amount of energy for it to be vibrating up and down that fast. Yes. Vacuum, absence of air and anything like space. Space is the vacuum. Vacuum means absence of any matter. It's only equal to that value when it's in a vacuum. If it's in a material such as air or water, the speed of light slows down. Alright, let's go over some examples on actually converting frequency and wavelength and finding energy. So what's the equation that relates speed, frequency, and wavelength? What's the equation that relates speed, wavelength, and frequency? So the speed is equal to frequency times wavelength. What makes electromagnetic waves, and in this class we're going to assume that they're all in a vacuum. So that means we're going to assume that the speed is going to be c, or 3 times 10 to the 8 meters per second. Yes, for on the homework problems and stuff, this is always going to be your speed, the speed of light, or speed of an electromagnetic wave. It's also, you can abbreviate this as EM wave. So this is our equation that relates frequency and wavelength to the speed. And the speed's going to be constant. It's always going to be 3 times 10 to the 8 meters per second. If we wanted to find energy of a photon, so energy of a photon, energy is equal to Planck's constant times frequency. So this is energy in joules. This is Planck's constant, also pronounced Planck's, depending on whether or not you pronounce it as German or the English equivalent. And its value is, so H is equal to 6.626 times 10 to the negative 34 joules times seconds. We're at PLANCKS. And then we have frequency, which will be measured in hertz. Now, this is the other equation. We can combine these two equations. So speed is equal to frequency times wavelength. If I wanted to solve for frequency using our triangle, speed is equal to frequency times wavelength. Frequency is equal to speed divided by wavelength. And so we can take this and plug this into E equals Planck's constant times frequency. So we can plug this F into this F. So E is equal to HV divided by lambda. Equivalently, since we know that the speed right here is going to be the speed of light, E is equal to Planck's constant times the speed of light divided by wavelength. So we can either write it in terms of frequency, or we can write it in terms of wavelength. So this one uses wavelength. And this uses frequency. We can also rearrange this speed formula. Speed of light is equal to frequency times wavelength. Alright. So let's answer some of these problems. You'll probably need another page. Again, we're doing this together. So yellow light has a longer wavelength than green light. Which of these colors has a higher frequency? So longer wavelength corresponds to smaller frequency or lower frequency. Shorter wavelength corresponds to higher frequency. So it says that yellow light has a longer wavelength, so yellow would be here. And green would obviously have to be over here. So green would have the highest frequency. So green light would have a higher frequency. Green light has a lower frequency than blue light. So now looking at green versus blue, green has a lower frequency, and thus blue has a higher frequency. So which one has a longer wavelength? Well, lower frequency means longer wavelength. So that would be green. So it works this way too. Calculate the wavelength of violet light with a frequency of 750 times 10 to the 12 hertz. So 700, you don't really need to know this as I convert it, times 10 to the 12 is a terahertz. So this is a terahertz, abbreviated as THZ. But if we wanted to convert this frequency into wavelength, so for number 3, we know that speed is equal to frequency times lambda. We know our speed is the speed of light, which we use the letter C to represent it. The speed of light is equal to frequency of the light times the wavelength of the light. We can make a triangle. C on top, frequency times wavelength on bottom. We are given frequency and we're trying to solve for wavelength. So we circle wavelength. Wavelength is C over F. So the speed of light is always 3 times 10 to the 8. Make sure you put this number in parentheses. Divided by the frequency is 750 times 10 to the 12. Make sure you put that in parentheses before putting it in the calculator. So always use parentheses when putting in a calculator around each number. And you'll get, the calculator should output 4e negative 7. Do not write it like that. Write it as 4 times 10 to the negative 7. So this number after the e is going to go on the 10. And this number before the e is going to be in front. And wavelength is measured in meters. So your wavelength is 4 times 10 to the negative 7 meters. Yes. So number 4. The frequency of yellow light is with a wavelength. Find the frequency, or calculate the frequency of yellow light that has a wavelength of 580 times 10 to the negative 9. 10 to the negative 9 is nano, so you're trying to find 580 nanometer yellow light, which is the same thing as 580 times 10 to the negative 9 meters. So again, speed of light is equal to frequency times wavelength. We're trying to solve for frequency. Frequency would be the speed of light over wavelength. So that's 3 times 10 to the 8 in parentheses over the this is the frequency, or this is the wavelength. So that's the wavelength. Wavelength is 580 times 10 to the negative 9, and put it in parentheses. And you should get an answer, 5.1724 E14. Do not write it in that notation. Instead, put it as 5.1724. Replace the E with a times 10. And put the 14 up as a superscript, very small up here. Frequency uses hertz. So wavelength is always going to be meters. So wavelength is always meters. And frequency is always going to be hertz. So yellow light is vibrating at crazy fast. And has a very small wavelength. So let's look at the next problem. Number 5. Calculate the wavelength of red light with a frequency of 460 times 10 to the 12 hertz. So again, keep this triangle ready. So we are solving for wavelength. So wavelength is going to be C over F. So 3 times 10 to the 8 over the frequency, 460 times 12, 10 to the 12. And use parentheses. If you don't use parentheses, you're going to get the answer wrong. So that would be equal to 6.52174 times 10 to the negative 7. This is wavelength, so it would be in meters. Seems easy, right? Speed of light is always going to be in the numerator. Frequency or lambda is always going to be in the denominator. So we're always taking 3 times 10 to the 8 and dividing by the other value. Number 6 is going to be the same thing. Calculate the frequency. Well, frequency is C over lambda. So frequency is C over lambda. C is always 3 times 10 to the 8. Or wavelength was 530 times 10 to the negative 9. And you'll get 5.660377 times 10 to the 14. And this is frequency, so you do hertz. I gave you this sheet. We can double check ourselves. So here is visible light. If we look at frequency, frequency should be around 10 to the 15, somewhere between 10 to the 14. So looking at this, so here's visible. Somewhere around 10 to the 13 to 10 to the 15 for frequency. And this is a visible light. Green light is visible. And we got an answer 10 to the 14. We can check on wavelength. So number 5 was a red light. Red light is visible. If we look at wavelength, let's look at another one. So here is visible right here. Wavelength is between 10 to the negative 6 and 10 to the negative 7. So we look at what we calculated. We calculated somewhere around 10 to the negative 7. Yeah, this was number 6. This was number 5. So one light beam has a wavelength of lambda 1 and a frequency f1. Another light beam has a wavelength of lambda 2 and a frequency of f2. write a proportion that shows how the ratio of wavelengths of these two lights are related to the ratio of their frequencies. So we know that, so we have one light that has a frequency f1 and a wavelength lambda 1. And that should be equal to c. And the other one has a frequency of f2 and a wavelength of lambda 2. That is also equal to c. So this and this are both equal to c. So we can set them equal to each other. This is so it's asking us to find a ratio or proportion of how the ratio of frequencies relate to the ratio of our ratio of wavelengths relate to the ratio of frequencies. We can to get a ratio of frequencies, we need to move this. Our ratio of wavelengths, we need to move this over here, so it's being multiplied on this side. So we can divide it on this side. This needs to be moved over to the other side, so it's being multiplied here. So we can divide on this side. And we see that the wavelength of the first light divided by the wavelength of the second light is equal to the frequency of the second light divided by the frequency of the first. So that would be your answer for that problem. Yes. Alright. 2 more examples. 8. So 8. No, we're doing this together. So number 8, the waves used in a microwave oven operate at 2.45 gigahertz. That all microwave ovens use this frequency. 2.45 gigahertz is the same thing as 2.45 times 10 to the 9 hertz. 2.45 times 10 to the 9. So our frequency of microwaves in an microwave oven is 2.45 times 10 to the 9 hertz. It asks us to calculate the wavelength of the microwaves in your oven. So wavelength is equal to, wavelength is C over F. So C over F, so that'd be 3 times 10 to the 8 meters per second over 2.45 times 10 to the 9 hertz. Make sure you put parentheses around it. And that's equal to 0.12245 meters. In centimeters, that would be 12.245 centimeters. But this is in meters, we use meters. So to give you the idea of how long the microwaves are in your oven, they would be from here to here. Let me actually pull it up. So here is 12.2. Here's that. Midpoint would be about right here. So this is literally the size of a microwave in your oven. If you remove the turntable from your microwave, sprinkle some cheese, and run it for about 3 seconds, It produces standing waves, so your food will melt right here and here, and right here and here. If you measure this distance, you should get somewhere around 6.12245 centimeters. And if we double that, that will give you the wavelength of the light. So this is something we can easily measure using a ruler, and because it melts the cheese, we can find out exactly its length. I'll try to do it tomorrow. Now let's go pass out homework now. I will. I haven't covered any examples of energy, so just skip every problem. You can work on. I've already explained the work formula. So every even problem asks you to calculate the energy of the previous problem. Remember, the end of the 6 weeks is Friday. If this is not turned in Friday, it's 0. I need to bring my data. So look at this real quick. Notice problem 2 asks you to calculate the energy of the previous problem. I haven't covered any examples of that. It should be straightforward on how to do. But tomorrow we'll work on some energy problem examples. You can work on it or wait. But remember, Friday is the deadline. If you don't turn it in Friday, it's a 0. If you're absent Friday, you should have it turned in as early as possible.